So now that we have found our appropriate ordinary differential equation for Q, the next step in our divide and conquer strategy was to find the final ordinary differential equation for P, where the way we had defined Q in the first place was simply as the product of this expected exponential behavior at large R times then the function P, whose equation we desire. The plan then is to substitute this Q into the equation for Q and then produce an equation for P. When doing that, as you can see, I need not only a term for Q, but also terms for Q prime and Q double prime. So let's stay organized and do these slowly, carefully, one step at a time. So Q prime is going to equal. Now, as we take these derivatives, much like in the derivation in the equation for Q, it really pays to constantly factor out factors that you know will always be there. And in this case, as we know, when we keep taking derivatives of exponentials, we keep getting the exponential back again. So I'm going to worry about keeping that factored out right from the beginning now. So let's factor that out. Now, when I take the derivative of Q for the first time, it's the product rule, derivative of the first piece times the second. The derivative of the first piece gives me my exponential back again, and a factor of minus alpha, and that, of course, is supposed to multiply the second term in the product, which would just be P. Next, I need to take the derivative of the second term. So I'll have the first term, which I've already factored out, and then it has to multiply the derivative of the second term, which will then give me just P plus, and the derivative of P, of course, is P prime. That's my Q prime. Okay, next, Q double prime. So Q double prime then is going to have, I'm going to try to keep this factor factored out. When I take the next derivative, I have to be a little careful now. I have a sum of two products when I distribute this out, and we're going to do them one at a time. So focusing on the first term in the sum, the first product in the sum. When I take the derivative of this product, the first thing I have to do is take the derivative of the first piece, which is the exponential, which will then give me my exponential back again, times an extra factor of minus alpha, which multiplies the remaining pieces. So when minus alpha hits these remaining pieces, I then have alpha squared times P. In the next term, I have the next term in the product rule. I'll have my first term already factored out times the derivative of the second term. And the derivative of the second term is fairly straightforward. It's just minus alpha times the derivative of P, which is P prime. Now, we really should leave a little space here because this second term is the term that usually gets doubled, just as we saw when we took a double derivative of a product in the equation for Q. So let's see how that would come about. So I've handled the first product in my sum, moving to the second product in my sum. When I take the derivative of the first term here, I will get my exponential back again, times another factor of minus alpha, which then multiplies the remaining term in the product, P prime. So I'm expecting another minus alpha times P prime, and I already have one minus alpha P prime, so this is the usual factor that ends up doubled. Finally, for the second product in my sum, I now apply the derivative to the second part, and that's a little bit easier. The first part is already written down, and the derivative of the second part would then give me plus P double prime. Great. So now we have Q, its derivative, and its second derivative. We are finally ready to insert into our equation for Q to derive the equation for P. When we're doing this, once again, we've been so careful to keep this exponential factored out again that I'm going to factor it out all the way from the very beginning into one giant overall factor. And now let's look at the remaining parts. So I have minus 1/2 Q double prime. So I need minus 1/2 of this product. The first term is already factored out, so I just need minus 1/2 times all of these terms. That gives me minus alpha squared on 2 times P, plus alpha times P prime when my minus 1/2 hits my minus 2, and then minus 1/2 P double prime, which is starting to look again like some kind of kinetic energy term. That's all from this first piece. My second piece then has a minus L plus 1 over R factor multiplying Q prime. Now Q prime has this exponential already factored out times these remaining pieces, which then have a minus alpha P plus P prime. good. Plus P prime, excuse me. Then finally, I have my minus 1 over r times q. The exponential, again, has been factored out, so I just need minus 1 over r on p. This looks like my potential, 1 over r times p. Very good. Close my parentheses. Acting on then my effective wave function p. Now, get myself a little more space. This all has to equal my right-hand side. My right-hand side is just e times q, so I've got e. Q again has this exponential factor, e to the minus alpha r times p. That again was quite a mouthful, but now the magic happens. This will simplify down at least a little bit for us. It really paid to keep these factors organized because now we can see immediately that they will cancel out. That we saw happen in the Q case. We also saw in the Q case a very nice extra cancellation, and the same type of thing is going to happen here. Right. The whole point of including this e to the minus alpha r term was that it balanced for us the kinetic energy term against the terms that survive as r goes to infinity, namely the e times q. So this e times p term we're hoping should cancel out against something on the left-hand side. Now the only p terms on the left-hand side are the last and the first. The last term has a 1 over r, and so it could never cancel the e times p. So we should concentrate ourselves on the first term. And there's a very good reason why this term and this term can cancel, and that's because they are equal. You might recall that at the very beginning of the lecture, when we talked about the value of alpha, we had written down actually the standard equation for our exponential constants alpha that we've been using pretty much for the last month or so in the course. This alpha is always written as the square root of twice m over h bar squared, but we are in natural units, so m over h bar squared is just 1, and then times the potential, and this alpha we derived for the large R case, and the potential at large R is just dominated by the Coulomb part, which actually also vanishes at large R, so the effective potential out there is just 0, and then it's potential minus energy E. So alpha is just root minus 2E. And then squaring this and dividing by minus 2, we also then showed, therefore, that the energy E actually does equal exactly minus 1/2 alpha squared. So that's just a little reminder from the beginning portion of the lecture. But now you'll notice this energy here is exactly the minus alpha squared on 2 term. That's multiplying a p. This is multiplying a p. So these terms do indeed cancel. So this term I can eliminate. This term then also cancels out, and all I'm left with on the right-hand side is just 0. So that basically gets me my equation. It's just now a matter of writing it down in a neat, organized form so that we can think about inserting the power series. So let's always go from more complicated to less complicated. So I'm going to start on the right-hand side then with the second derivative term. So I have minus 1/2 p double prime. And that's kind of nice, right? That feels like a typical kinetic energy type term. The next type of term I have is I have over here, a little complicated, is p prime over r. So let's separate that out. So there's a minus L plus 1 times p prime over r. That term shouldn't be too mysterious to us because actually that's the same extra price we had paid. It looks like the very same structure that we had paid when we had eliminated the r to the L plus 1 pieces when we used and derived the equation for Q. So this is kind of expected. Let's continue on. The next most complicated thing, I think, is the p prime term. So there's this additional cost we've paid for this nice cancellation of the energy term by making this extra factor into the definition of our function. And that additional cost is this alpha p prime term. Let me just underline these terms as I've taken care of them so that I don't lose track of what I'm doing. Then the next level of complication that's left to me is, I see I've got actually 2 terms that are p over r. So let's factor out those. So there's a p over r, and there'll be a parentheses. And there are 2 of these p over r terms. There's the piece that looks just like my Coulomb potential, the minus 1 over r. So let me write that out a little bit special. over here. And then lastly, I've got this extra cost paid for including this alpha factor. It comes in with a plus sign, a P over R. So here's a P over R. That one's coming in with a plus sign. And the remaining parts, aside from P on R and the plus sign, is alpha times L plus 1. And that was that additional piece that we had up above, so I should include it here. And all of this then, therefore, has to equal 0. And that then gives us our final ordinary differential equation for P that we were tasked with actually deriving. So let me put a nice box around that, because now we can quote this result and use it to continue our analysis with the power series.